Muy bien, estamos listos. Vamos a esperar unos minutos a ver si regresa Moisés. Hola, Moisés, buenos días. Están jugando a las escondidas. Estabas tú, te fuiste, llegó Salvador, se fue Salvador, tú llegaste. Este, eh, tu audio no lo escucho bien, se escucha muy quebrado tu audio.
¿Qué tal ahora?
Ahora sí ya, mejor.
Ya, ok, ya. Sí.
Muy bien. Bueno, vamos a esperar unos minutos a ver si se puede conectar Jesús.
Ok.
Ya regresé.
Ya. Se pusieron de acuerdo ustedes. Tomarse turnos. Muy bien, entonces vamos a iniciar. So let's start now. So first, I'm going to give you a review of what we have seen so far, and then we will continue with something that we left unfinished last time. So, right, so basically we have seen the definition of a manifold in terms of the atlas. And so we saw some considerations that we need to consider to define a manifold in terms of an atlas. Then the next thing that we covered was the tangent space at a point. Which we denoted like this. For that, we consider the germs of functions at P. Also, then we saw that the vectors are derivations. And so we have two ways of thinking of this in terms of curves, the geometric way, or derivations. the next thing that we cover, we are basically on the same kind of ideas, submanifolds. The definition of a submanifold, and there are two aspects to consider here. One of them, so you have an ambient space, and we describe what subsets are submanifolds. So that's an important thing to consider, subsets that behave like a manifold. So that's one thing. And the other aspect that it is important to us, submanifolds on their own are manifolds. So we have another approach of generating new manifolds, right? Because basically what we covered at the beginning in terms of manifolds, we have open sets, the Cartesian product, and also we managed to construct new manifolds using the quotient. We managed to see the torus, the Klein model, and so on. Right, so we managed to talk about some manifolds. Now, in order to, the way that we have you can think, why did we study something like this if we are going back again to study manifolds here? Well, it's because some of the results that will help us to get new manifolds or submanifolds are in terms of the rank of a map. So we have seen for any smooth map, we have a linear map between finite dimensional spaces, vector spaces, like this. And so this, understanding this, also we have several results that we have seen before and we'll see today that will give us example of manifolds. So that's why we study in principle this first, so to apply all of these results. Very good. So later on, so basically we are still at the same level, just manifolds. But I don't know if we will study this today or tomorrow. Remember when we define the tangent space, usually that's only vectors at a point. But when we were discussing that, I said something very little about vector fields. We haven't studied those in detail, we will. In particular, we will study the tangent bundle. Okay. So far we are only at the first stage, yes, manifolds, submanifold, and smooth maps. Now, also something that you can consider with this subject, part of the mathematics or the mathematical problems is try to classify all manifolds. So that's a very naive thing to do in higher dimensions, but that's more or less the spirit in this way of thinking. Another important problem is if you have a manifold with some nice features or additional features, what kind of submanifolds can you have there? So those will come later on. But I just want you to focus on what we have done. And the reason that we went here is try to get more examples of this, or of submanifolds or manifolds. Okay, so last time, remember that we were looking at the constant rank theorem between manifolds, and I told you that it relies on the same result, but on Euclidean spaces. And this is what we will prove today. So we have a smooth map between open spaces in Euclidean space, and we assume that we have constant rank in a neighborhood of E. Then we can change the coordinates of these two spaces so that the function looks like this. Basically, if I have constant rank, it is just a projection. Okay, that's the whole idea of this result. So this is what we will prove. The same also holds for a smooth map between manifolds, but we will just cover this this feature here. So before going into the details of the proof, I just want you to try to more or less give you an idea of why this is true. Just remember, this is a local statement. This holds in a neighborhood of a point only. It's not global. So imagine that you have a function between R3 and R2 of constant rank 1. Remember that this means that the differential at any point is a linear map of rank 1. Oops, this is wrong. Like this. Right? Now, you can very well imagine three-dimensional space at any point. The tangent space is three-dimensional, and you have a function into R2. If you have a point here, this is f of p. So if you think about this, what you have At P, you have the tangent space, which is three-dimensional. Because you have a map of rank 1, that means that the image is going to be a one-dimensional space, subspace, on the tangent. Right, so this is a three-dimensional space. And in here, the two-dimensional space, you have a line. Now, this behavior not only happens on P, but happens on nearby points about P. So the three-dimensional space is collapsed into a one-dimensional space. So now let me, so I don't know, if you take points nearby P, you will have something like this, and so on. Only lines. Those lines that I draw are on the tangent space of that point. Now remember that we have a way of computing this in terms of curves. You take a curve that goes through P, the derivative is some vector, and you push it forward, that vector is going to lie in this line. That is, so now I'm going to erase the subspace, and I'm going to draw the image. So the image will look something like this, locally. Just one-dimensional space. Okay? So that's exactly, I mean, let me draw it even straight lines, so to speak. This is what we are saying here. Only K parameters move, and the rest don't move. So that's more or less what is happening here. And you can also argue in the same way from R2 to R2. The only difference, here you are collapsing a three-dimensional space into a one-dimensional space, and here you're collapsing a two-dimensional space into a one-dimensional space. So actually, the result that we're going to prove, we're going to consider this particular space. Okay, so we're going to prove this result. So I have a point such that the function, the smooth function f, has constant rank. And what I'm saying is, nearby I can find coordinates so that the function looks like this. This k is the rank of the map at P or nearby. Great, so let's prove this. Again, so I will do it in a particular case only when we have from a map from two-dimensional to a two-dimensional manifold, and I will assume that we have rank 1. Right? And I will take the 0 point to be the point P. So we have constant rank in a neighborhood of 0. Well, we have f1 and f2, the coordinate functions. I look at the Jacobian matrix, and my hypothesis, in a neighborhood of 0, this matrix has rank 1. Okay? So I'm going to assume that in a neighborhood of the point 0, this will never vanish. Okay, so I mean, I know that at least one of them will not vanish because I have rank 1. So I will assume that it is the first one. It doesn't vanish, so in a neighborhood of 0, I'm going to call it U0. So the partial derivative is non-zero there. Okay? Now, I'm going to consider a new function defined like this. So this is a neighborhood of the 0 point where f has constant rank 1, or this is non-zero. So I have that map between R2 and R2. So basically, I would like G to be a coordinate chart in U or a smaller set in U. Right? Okay. So G is a smooth map because F is. I look at the Jacobian of this function, and I have this expression there. Right? Now, this doesn't vanish on U0. And the determinant of that matrix is precisely only this term. So the linear map has determinant 1. It is a non-singular matrix. Okay? So it's non-singular here. And we have seen this before in the inverse function theorem. If I have a smooth map which is non-singular at a point, then in a neighborhood of that point is a diffeomorphism, like the inverse function theorem. The same in calculus of a single variable. If the derivative is non-zero, locally at that point, I have an inverse. So maybe in a smaller set, G is invertible, and I will call it F. Okay? So maybe I have to shrink my domain. So I have U1, a smaller set that contains 0, and where G is invertible. Okay, now let's compute this. We know that it is the identity. And from this, I would like only to recover this. Let me go up just to remind you the definition of G is there on the top. G is F1, y. here is G, F1 and Y. Okay then. Thus, I'm going to keep only this part. That equality here, that's the important feature that we want. So I have this relation that comes from this. And that relation is the one that I would like to keep. Okay? Now, so let me compute my initial f with the inverse. Right, so I just applied the definition here. And then this comes from this. The second entry is the same. We don't do anything whatsoever. Right? So far so good. Right? Look, I'm applying this function to u comma v, and I'm getting u and something else. So we are halfway there. Because remember what we are aiming at. I want to be something like this. U comma v. We are assuming rank 1. So far, I have the u. So I need to change a little bit more to make this equal to 0. Well, not that. I mean to make the second entry 0. Okay? So let's move on then. Well, this is, yes, I rewrote the same equation that we have. Emphasizing that here I have this, nice, but I must change this. Okay, then, now, G is a diffeomorphism. So the differential is a linear map, which is non-singular. On the other side, F, we said it has rank 1. So this function has rank 1, but now on this point, right? Okay. Now, I'm computing here the differential of the inverse. But why is that? I don't see why did I wrote that. Why is that? Okay. Right. No. There's a mistake. Right. Sorry. I want to compute the Jacobian of this. I forgot to write the f there. Because I take the derivative of this with respect to u, 1. With respect to v, 0. This with respect to u, and with respect to V. So there's some mistake here. I'm not computing the Jacobian of G inverse, but of F composed with G inverse. So sorry about that. This is F. Okay? So of this function, right? So again, let me repeat this. So we have the function on the red rectangle. We know that it has constant rank 1. And we compute the Jacobian. So with respect to U, I get 1. With respect to V, I get 0. And I look at the second entry and take the partial with respect to U and V. Okay? So far, so good? Now,
Yep.
nice. So here I have two things. Rank 1 and the Jacobian. How do I compute the determinant? This times this minus 0, right? If I want to compute the determinant of this matrix, it will be this minus 0. So the determinant of this matrix is this entry. However, I'm saying that it has rank 1. So that entry must be 0. Right? Because on one hand, I'm saying that I have rank 1 on a 2 by 2 matrix. So the matrix must be singular. It cannot be non-singular. Otherwise, I will have rank 2. So combining those two observations, I get that this is 0. So that function doesn't depend on V, only on U. And I will write it like that. This function only depends on U. Then I'm rewriting the red square and the green square. It's the same equation. I'm just saying renaming the second entry. That's all. And then we are done. Let me just, I made a mistake here. I don't want to call it F because I said that F was G inverse, so let me call it F0. I'm defining this new function. Okay? And let's make the composition. This, we know it is here. And now if we apply F naught, that's the definition of F naught, we have what we were aiming at. Okay? So basically, the inverse function theorem helps me to get the first entries equal. That's what we got here. This equal to that one by the inverse function theorem. And then once again, we rely on the rank of the map to make the vanishing of the other entries. Okay, so this is the proof of the constant rank lemma for Euclidean spaces. Right, and that's the whole idea of making this the same ones and then 0. And again, so this, we just focus this on multivariable calculus. I avoided using the concepts that we have learned in this class. So this is the same statement but on manifolds, because it is a local statement. So we can find the shards. For this, we use the inverse function theorem, and then we need to make this 0. Okay, and the whole idea of this theorem, to recall this, and what actually drove us to consider those results, is this statement. The whole idea is to try to understand when the pre-image of a point is a submanifold or a regular submanifold. First, we saw the case that the pre-image of a regular point will give us a regular submanifold. And this is the other statement. So here I only require that F has constant rank in a neighborhood of this. And then I can conclude that I have that the pre-image is a smooth manifold. And not only that, we note the dimension, which is going to be the dimension of n minus the rank. Okay? So this is the goal that we were of all our previous work for this result. Okay, then, so again, we saw that the pre-image of a regular point is a submanifold. When we saw that result, we even saw some applications. Among them was that the SLN is a regular submanifold, the special linear group of matrices. We saw that that was a submanifold. And so now let's see an application. We saw this last time, so but again I will cover this. So there's nothing new about this. This is the same. The same example than last time. So we consider this function like this. Now, well, let's continue. So I take this is a smooth function because the entries are polynomial functions of the entries. And moreover, we know that the preimage of the identity is going to give us this. Okay? Now, I want you to consider this. I mean, remember that this is an open set. This is an open set on Euclidean space. So the derivatives that we will take, they will be the same as in the case of multivariable calculus. There's nothing different there. However, this result, you didn't study this result in multivariable calculus, and this will be one of the reasons. So, look. So we are here. On inside GLN has the preimage of the identity matrix. What can you say about OM in terms of topology?
It's open and connected.
Is
Open and connected.
okay. Why do you say that it is open? Salvador?
ON was SL, right?
ON was?
SLN,
No,
or am I?
they are different. SON is different from ON. The special linear group are all of the non-singular matrices or matrices, whatever, such that the determinant of X equals 1. So the S on all of the linear groups, whenever you see an S, means determinant 1. So this is the set. Again, I'm going to say non-singular, such that X times X transpose equals the identity. That's the definition of ON. Now, this in terms of the rows or columns of X, what can you say about it? Because I have this. This is X time X transpose. So I'm going to write it like this. Say here you have V1, a column vector, V2 up to Vn. So now that vector, think about it like this, is V1, V2, Vn. This is equivalent that the rows of the matrix X is an orthonormal basis or orthonormal vectors with the standard dot product on Rn. So this is the standard inner product. Okay. So that's what a orthogonal matrix is. The rows are an orthonormal set. And the same for the columns. It works for both. Okay, so, well, let me write one more. SON is an orthogonal matrix such that the determinant of X equals 1. Okay? And last week, or I don't remember when we covered this, I think Moises gave me an example of a matrix here that is not here. So an orthogonal matrix that is, whose determinant is different than 1. So this is a proper subset of this, right? Good. Now, let's get back to this. So the set of orthogonal matrices is a proper subset of the group of non-singular matrices. Now, I have said that this function is smooth. In particular, is continuous. Hence, this subset is a closed subset on GL. Okay? So this is closed. It's closed in GL or also in the set of n by n matrices, because GL is open there. So the set of the group of orthogonal matrices is a closed set. And is not connected because an element here can have determinant -1. And we covered that in order to go from -1 to 1, you need to move through the 0. But there are no orthogonal matrices of determinant 0. They are all non-singular. So ON is not connected. Okay, so those are a few topological features of ON, right? So it is closed and not connected. What we saw last time is that we can factor this function like this, using the left and right multiplication, where A is any matrix. Okay, or if you want, evaluate it at B. So for any matrix A and B, you have this. Now, when we studied smooth functions, we saw that the left multiplication and right multiplication are diffeomorphisms on any group. So again, this function is a diffeomorphism, diffeo and diffeo. Okay? Now we compute the differential of this map. So I have the differential at V. We use the chain rule. So here is at B, here is going to be at, I think I wrote it wrong here, sorry about that. So here is F, the differential here is at F of B. And the differential here is the right AT, right? That's the differentials. Because it is a composition. So from B, I got to F of B, and from this, F of B times A of T. The same way here, compute the differential at B and then left AB. Okay, so I can compute the differential using the chain rule. And now this linear map is non-singular, this is non-singular, this is non-singular. Hence, the rank of this map, which is the same as this one, means the rank of this is the same as the rank of this. Where A and B are any non-singular matrix. And that's what I have on the green rectangle there. But I mean, this is telling me that the rank at any 2 points is the same. you just need to rewrite A and B like this. I take two matrices, and I want to show that the rank here is the same as the rank there. So I put A0, and then I choose B. I'm sorry, I choose A to be this. And this is precisely the rank of F at A1. Okay, so the rank at any 2 points is the same. So that means that F has constant rank. Not only in a neighborhood of the preimage of the identity matrix, but on all of the domain. It has constant rank. Okay, so with this, we have that On is a smooth manifold. Okay, I have that. Any questions or comments up to this point? No? Okay then. Let me just move this. Well, this is what we saw last time. And now, in order to determine the dimension of On, I need to know the rank of the function. Okay? So far we only use this decomposition. Oops, sorry. And then we use the chain rule, and that's it. Just to find that we have constant rank. That's all the knowledge that we use here. So now we need to find the value of the rank. Since the rank is the same at any point, I will take the identity and try to find the rank of this linear map. Now, basically, up to this point is all that we need about what you have learned in this class. The rest has to do just with multivariable calculus. And that's what I'm trying to emphasize here. This is open. So the tangent space in GLM is the same as the tangent space in Rn squared. So basically, what we are studying here, one way to compute the rank is to find the Jacobian of that matrix and compute the rank. That's one way of doing it. The way that I will do it is using the differential that we have used before. But in terms of multivariable calculus, I will take a curve. That curve will be on Euclidean space. And then in order to compute the differential, we will take the derivative in the usual way that you are used to doing it in Euclidean space. So there's nothing new. The only thing is the concept that we are computing the differential. Other than that, it's just computing derivatives in Euclidean space. Okay, then. I would like to find the dimension of the image of this map. That's the rank. In order to do so, I'm going to take a basis of this space, linear algebra. Because it is more convenient not to write the vector all the way row or column, but it is better to express the vector in terms of a matrix. So this is going to be my basis vectors. Okay, note that we have n squared. N squared vectors, which agrees with the dimension of the Euclidean space Rn squared. Thus, to compute this, I will use the method of a curve. I will take an element of the basis, a curve that goes through the origin, and such that the differential is the prescribed vector. Then I will compose with the function f, so I will know what is the image. So we compute the differential using curves. Okay, so we are going to do it two ways. First, when my vector has a 1 in the diagonal, and then we will do the case when the 1 is outside the diagonal, and try to determine what is the push forward of that vector. Okay, so let's consider this function here. I'm going to consider this vector of the basis. It has a 1 somewhere in the diagonal. So this is one of these vectors. And the curve that I'm considering is this one here. Okay, now I don't know why did I put t minus 1 here. Let me erase that. Right, now at t equals 0, I'm at the identity. All right, I know why. This curve has to lie in the non-singular matrices. So the determinant has to be non-zero. That means I just need t to be different than minus 1. Otherwise, the curve will go outside of GLN. But again, I only care about a neighborhood of 0. Okay, so I have a curve here. At 0 is the identity, and the derivative is this vector. So in order to compute the push forward of this vector, I compose the function with the curve. So now this is a curve also on GLN, but let's say not on the domain, but on the codomain. And you can write down the product and you have something like this. Then, if I would like to find what is the vector corresponding to that curve, I need to take the derivative and evaluate at t equals 0. And the way that we compute the derivative of a matrix is entry by entry. The same way in calculus. Usually you have a row or a column vector. Here the arrangement is different, but again, just entry by entry, we compute the derivative. Evaluating at 0, I get a 2. Hence, this differential looks like this. So this vector on the tangent space is going to itself, but with a 2. For this purpose, it's not important, but basically we found n eigenvectors. Okay. Any questions on this? Jesus?
Not yet.
Okay. So we computed the differential. I mean, this is just our notation that we have learned in this class, but know that all of the procedure is multivariable calculus. Okay, so with this, I have that the image at least has dimension n. Okay? That's the goal, to determine the rank of that function or the dimension of the image of that linear function. So we will continue with this. Now I will consider when I have a 1 outside the diagonal. I would like to have a curve and also a curve to the origin such that the derivative is that vector. So this is the curve that I take. Once on the diagonal, and I have a t in the entry ij. Okay? Don't play with your cat. So when t equals 0, I have the identity. The derivative, this is constant, so I will only get a 1 here. It is this. Right, so that's the derivative. Now, something that I didn't wrote here, but this C of t, every matrix is non-singular. Right? The determinant of that matrix is non-zero. I think the determinant is even 1. Determinant 1. Okay. Now, I would like to push forward this vector under F and see what do I get. So we use the curve is the curve times the transpose. So this entry is in the ij, and then it goes to the ji. If you compute that product, you will get something like this. This is in the ij, and this is in the ji entry. And then here you will get on the diagonal that one. Now I'm puzzled about this. Is this right? This equality? I mean, basically, I'm having trouble. So this is like this. But here, do I get one or something different? I don't know if I made a mistake there. Let's see. So 1 plus d squared t oh, it's correct, right? So I think it's right, yes. So yeah, I was puzzled about this entry here, if it was 1 or not, but it is. Okay. So we have that curve. Know that at 0, as expected, we have the identity matrix. So now we need to take the derivative and evaluate at t equals 0. The derivative is entry by entry. Evaluating at 0, you get this. So now instead of one entry being filled, you have 2 entries. Okay? Up to this point, any questions? So notice the following, that so what is the image in terms of matrices? The first part, I can have whatever I want here. Anything that you want. So that was the n entries that we had before. But now on the other ones, if you put here 1, 2, you must put here the same value, right? this is what we conclude from this computation. So that's how it goes, and so on. So basically the image are the symmetric matrices. And that's precisely the dimension right? Because the only three parameters is the diagonal, and you can go either up or down. So n times n plus 1 over 2. Those are the three parameters to determine an element in the image. Hence, the dimension is the dimension of the space minus the rank. And this is the answer. So that's the dimension of ON. Any questions?
So, what? Why was this the image of the differential?
You mean here?
Yep.
Okay, right. So on part A, we computed of a matrix like this, a 1 somewhere in the diagonal. And we show that this is twice the same vector. On part B, we computed, we put a 1 anywhere outside the diagonal. Anywhere. Here. Okay. And we show that this is one and 1, symmetric. So we have computed this for all possible vectors in the basis. Here I have n possible vectors, and here the remaining ones. In total, the dimension of the tangent space is n squared. So it's just, we put zeros everywhere and a 1 in one of the entries. And that's how we compute the standard basis. Now, so putting together all of this, we know that the image of the linear map is going to be expanded by this. So over the reals, these are real linear spaces, the span of all of these matrices. Etc. And then 0, 1, 1. Do you agree on this equality?
Yes, I do.
Right? Because I computed the linear map now on all of the basis elements. So I have that equality. But all of this, because it's over the reals, I mean, I can say this is 1, 1, and 1. I don't care. But the span of all of these matrices under the sum of matrices is precisely this. On the diagonal, I can put whatever I want, but outside the diagonal, it has to be symmetric. This is taking care of the diagonal, and outside the diagonal, I get this. So that's why I'm saying that the image is given by this. Is it clear, Jesus?
Yes, thank you.
Okay. Now, the other part that I would like to emphasize here, again, the computation that I show you, I tried to do it like Euclidean space, vectors, but with a different array, a matrix array, not columns or rows. But so if you have, let's say, I don't care if they are non-singular or not. I have two curves of matrices. I want them to be squared just so that I can make the product. When I took the derivative in these two cases, I did the product and then compute the derivative. It was very natural to do it, but also the product rule also holds. If you would like to take the product of two matrices and make the derivative, this is what you expect. This is the usual product of matrices, and the dot means you are just taking derivatives entry by entry. Okay, so that also holds. But I decided just to go ahead, do the product, and then compute the derivative. Again, here I have the product and then compute the derivative, but you can do it the other way around also. And in fact, later on, we will use this formula. Great. So then, ON is a regular submanifold by the constant rank theorem, and the dimension is the dimension of the ambient manifold minus the rank. We just computed the rank here, and we get the dimension of ON. Any questions?
Nope.
Moises? Moises? Any questions?
Nope. Nope. Super seguro.
Now, when n equals to 1, what's the dimension? Anyone? For n equals to 1, what is the dimension?
0.
0. And for n equals to 2?
1.
Okay. Now, this is right. I mean, because you are talking about 1 by 1 matrices of determinant 1. I'm sorry, not determinant 1, that's Sn. Sorry, SON. You want A times A equals 1. Right, remember that we have A times A transpose equals the identity. When n equals to 1, this is just real numbers. So you want A times A equals 1. So which numbers satisfy that condition? A squared equals 1. So O1 is just two numbers, minus 1 and 1. This has dimension 1. We have said several things about manifolds of dimension 1. Do you remember?
I didn't get that. Can you repeat it?
Yes. I have said what are all the manifolds of dimension 1. It is a very short list of all possible manifolds of dimension 1.
The line and the circle.
Right. We haven't proved it yet, but the only manifolds, connected manifolds of dimension 1 is the line and the circle. So in this case, O2 is going to be 2 copies of the circle. One of them will have determinant 1, and the other, so here is the identity, and the other one will have determinant minus 1. So in other words, SO2 is the circle. Okay. So let's move on. So we have seen smooth functions between manifolds. We take the differential. And we have seen this, again, as I said at the beginning, to try to obtain new manifolds, or more precisely, submanifolds of M. Now, in some cases, it is good to have these concepts. A submersion is a smooth function such that the differential is surjective for every single point. A function like that is called a submersion. And in last class, we looked at this example in detail, what happens with the differential, which is just the projection. ddx and ddy project to themselves, and ddc goes to 0. So this is an example of a submersion. More generally, is this map, the projection, the one that you study in one of the homework problems. Like this. Another example of a submersion is the tangent bundle and fibrations. We haven't seen those, but maybe today we will start looking at the tangent bundle, if not tomorrow. But the tangent bundle is an example of a submersion. On the other side, we have the concept of an immersion. An immersion is a smooth map such that the differential is always injective. Okay? So notice that for submersions and immersions, we have constant rank, depending on the dimension of n and n. It will be, depending if you have a submersion of an immersion, the rank will agree with the dimension of the domain or codomain. An example of immersions we have seen also in the last class, the inclusion. Remember that we see this example last time. ddx at the point x comma y maps also to ddx, but now in the point x comma y comma 0. More generally, an inclusion at the level q is also an example of an immersion. Another example is the one that appears in the problems of some manifolds, the graph. If we look at the graph, this is as a manifold, the graph of a smooth function, and that's also an example of an immersion. Note that I have an immersion in this map. I'm not saying that this is an immersion. Right? And well, those objects are important on their own. We will not see so many of that, except in the case of submersions, for the tangent bundle and fibrations. We will study tangent bundles and also vector bundles, which is something more general than tangent bundles. So for the last 10 minutes, let's try to see a little bit about tangent bundles. We will not have time to see the dimension, but we have enough time to have a feeling, because also this is something that not in this main, but you have seen it before in multivariable calculus. So that's why I'm making the example to be Rn. Right, so we have Rn, and for a point, we always have the tangent space. And in this case, in Rn, we have global coordinates, and we know very well how to describe the tangent space. If I'm not in Rn, but I'm in a manifold and a chart, we have also seen how to describe this in terms of the chart. Okay, so the whole idea of the tangent bundle is to put together the manifold and the infinitesimal information. Remember that the infinitesimal information is the tangent space. So this is something for you, not complicated, just Cartesian product, but this is going to be our tangent bundle for the case of Rn. The first entries corresponds to a point in the manifold, and the last entries will correspond to a vector on the tangent space of that point. Okay, so this is the crucial part. This is not any vector. It is a vector that belongs to the tangent space of this point. So they come together like this. So if I have a point, this vector, usually written like this, in the notation that we have been using, corresponds to this. Okay? So Rn times Rn, this is the notation that we will use, and that's the tangent bundle of Rn. So we are putting together all the tangent space of the manifold. So again, it's important to think that the first thing is the manifold, and the second entry corresponds to the tangent space or the linear space. Manifold and linear space. In terms of sets, the tangent bundle is the union of all the tangent space, where the point varies on the manifold. So for Euclidean space, it's very easily, it's just the Cartesian product. But we will describe this, the tangent bundle, for manifolds. Let me take this picture from here. Usually, we would write the tangent bundle or vector bundle like this. We have M on the bottom. We will write a square on top of it. And the idea is, if I take a point here in my manifold, I have a line that represents P of my manifold. Let me put it Rn. Okay? And moreover, so I mean, here we have a projection map. Because on top, I have P, comma V, and I projected the P. So above each point, I have the tangent space. So note that the pre-image of every point is a vector space. Not only that, that vector space is Rn. So for every point the pre-image is always the same. And this is what it is called the fiber. In this case, it's just the vector space. Okay, so this is the tangent bundle of Rn, and this makes perfectly good sense for you, but I would like you also to try to get used to this. This notation is the most common use, not only for tangent bundles, but for any vector bundle or any vibration. The target, which is M or Rn, you have it here, the target of the map. The reimage of every point is always the same. And that's what is called the fiber. In this case, it's just the tangent space at that point, but all of them has vector spaces are just Rn. Okay, so let's move on. Let's do the what happens in general. The way that we will do it is the following. Has sets, there's nothing more to be said. It's just the disjunct of this. Nothing new. However, here I cannot write it like M cross Rn. That's not true. Okay? And then the whole idea is the tangent bundle is in fact a smooth manifold. So that's what we are going to see next time. That this is a smooth manifold. So, and the way that we will prove that it is a manifold is by giving shards. And the shards that we will define on Tm are going to be induced by the shards on M. Okay, so tomorrow we will look at the local picture, meaning we will take a shard and just look at what is the tangent bundle of that shard, and then we will construct the tangent bundle at M. Great. So for this, we are done for the class. Are there any questions?
So far, so good.
I'm okay too.
Okay, so see you tomorrow then.
Oh, and let's remember that.
Yeah. Let me
All right.
just
See you tomorrow.
see you.